Hi, this is Stu Schwartz from MasterMathMentor.com. This is video BC15a. The topic is Taylor polynomials, and it covers the BC manual pages 77 through 82. This cartoon probably doesn't make much sense, but it will by the end of this video, and we will come back to it. This video is on Taylor polynomials. It is the first concept in the final section of BC Calculus on infinite series. The course now becomes quite different, focusing less on practical applications of derivatives and integrals and focusing more on theory. One of the results of this study is to understand what goes on under the hood of our amazing graphing calculators. So be prepared for new notation and new vocabulary as we study this very different branch of calculus. Suppose you are asked to find the sine of 37 degrees. We can do this easily on the calculator, but there are two big questions. First, what is it that you're actually finding? And secondly, how does the calculator find it? The first question is easy. If we draw a unit circle with central angle 37 degrees, we have a drawing with hypotenuse equal to 1, and therefore the sine of 37 degrees is equal to y over 1, and sine of 37 degrees is equal to y. So when we are finding the sine of 37 degrees, we are finding the side opposite 37 degrees in a right triangle with hypotenuse 1. So how does the calculator actually find the sine of 37 degrees? There are two possibilities. The first is that it has the 10 decimal values in the answer memorized. Now, if we assume that the calculator can take trig functions of angles from negative 1 billion to 1 billion degrees, with angles accurate to 6 decimal places in between, that would be 10 times 2 times 10 to the 9th times 10 to the 6th, or 2 times 10 to the 16 bytes of information, which is 20 million gigabytes of memory. That clearly is impossible on a small machine. So the only other possibility is that when you press the sine button on the calculator, it is actually going through some process to calculate the sine of 37 degrees. That's not far-fetched. When you press the accelerator in your car, that doesn't actually make the car move. It starts an internal process with many steps under the hood, but ultimately results in the car moving. The same type of thing will occur when you find the sine of 37 degrees. There are some preliminary facts that we need before we get into the important part of this section. It may surprise you to know that even the most sophisticated calculators, including your graphing calculator, is capable of only 4 operations: addition, subtraction, multiplication, and division. Yes, it can do trig functions, square roots, logs, and exponentials, but these are simply a series of these 4 arithmetical operations, as we will see. So this section of the course will be much more different than anything we've covered before because we're going to focus more on theory. Also, there's a fact used primarily in probability theory that students should know, and it's the concept of factorial. We define n factorial, written with an n and an exclamation point, as n times n minus 1 times n minus 2 times dot 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 times 3 times 2 times 1. So 4 factorial is 4 times 3 times 2 times 1, which is 24. 5 factorial will be 5 times 4 factorial, which is 5 times 4 times 3 times 2 times 1, which is 120. Factorials get huge. 10 factorial is 3,628,880. and 15 factorial is over a trillion. The largest factorial that your calculator can take is 69 factorial, which is almost 10 to the 100th power. We will define 1 factorial to be 1 and 0 factorial to be 1 as well. Suppose we have a function, f of x equals 16 square root of x, and we would like to find f of 1.2. We have a graph of the function, and we could estimate the value of f at 1.2. But suppose our calculator did not have the ability of taking square roots. Early calculators in the 70s only had the 4 functions: addition, subtraction, multiplication, and division, and cost hundreds of dollars. A square root function, when it came out, added many dollars to the price of a calculator. So it is not as far-fetched as you might think. How can we come up with a good estimate for the value of 16 times the square root of 1.2? Now consider the polynomial function p of x equals quantity x minus 1 cubed minus 2 quantity x minus 1 squared plus 8 quantity x minus 1 plus 16. It is shown on the graph in blue. Notice that at x is equal to 1.2, the blue polynomial is a terrific approximation for the red function, f of x equals 16 square root of x. If we plug in 1.2 to that expression, we get 0.2 cubed minus 2 times 0.2 squared plus 8 times 0.2 plus 16. This can be calculated with a series of multiplications, additions, and subtractions, and we get an answer of 17.528. So it should be obvious that the blue polynomial function is an excellent estimator for the red function around x is equal to 1. The value of the 16 times the square root of 1.2 is 17.52712,184. So the difference between the polynomial and the actual value of the function is less than 1/1000th. Anywhere around x is equal to 1, the two will be very close to each other. But as we get further from 1, approximately around 0 or 2, notice how the graphs start to separate. We call them diverging. So the question is, if this polynomial is such a good estimator, where did it come from? That is the subject of this video. When we did linear approximation in AB calculus, we used the premise that a line was a good approximation for a function around a point. The value of the function and the line must agree at that given x value, and their derivatives must be the same as well. So to find a polynomial function p that approximates a function f, we begin by choosing some number c such that the value of f and p are the same. That is, f of c must equal p of c, as we can see in the graph. In addition, at c, the derivatives, the slopes of the tangent lines of the two functions must be the same. That is, f prime of c is equal to p prime of c. If that is true, we say that the approximating polynomial p is expanded about or centered at c. Let's see an example of this. We have a function f of x equals e to the x, and we would like to find a first degree polynomial function p of x that will be a good approximation for f of x at the point where we will center it at x is equal to 0. We are going to call this p of x equal to a1x plus a0, which of course is a line. And we would like its value and slope to agree with the value and slope of f at x is equal to 0. Now, normally when we talk about a line, we talk about y is equal to mx plus b. I know you're not wild about using the coefficients a1 and a0, but there is a good reason for using them, as you will see later. Our first condition is that f of 0 must equal p of 0. F of 0 is equal to e to the 0, and p of 0 is equal to a0 plus a1 times 0. And that means that a0 is equal to 1. That means that our polynomial p of x is equal to 1 plus a1x. Our second condition is that the derivative of the f function must be the same as the derivative of the p function at x is equal to 0. F prime of 0 must equal p prime of 0. F prime of x is still e to the x. P prime of x is equal to a1. So that means e to the 0 equals a1, and that means a1 is equal to 1. So that means that our polynomial is p of x equals 1 plus x. So now we include our polynomial function p of x equals x plus 1. At x is equal to 0, the two curves meet. And around x is equal to 0, the red p of x is a very good approximation for the black e to the x. However, the further you get from 0, the more the two curves diverge. And when you get much further than 0.5 away from x is equal to 0, the red curve will no longer be a good approximation for the black curve. So now let's use a quadratic to approximate our function. We will call this quadratic a polynomial and call it p2 of x equals a2 x squared plus a1x plus a0. Our function is still f of x equals e to the x centered at 0. Now there are three conditions. First of all, the polynomial and the function must meet at x is equal to 0. P of 0 equals f of 0. Secondly, they must have the same slope at x is equal to 0. So p prime of 0 equals f prime of 0. And finally, they must have the same concavity at x is equal to 0. So p double prime of 0 equals f double prime of 0. For condition 1, p of 0 equals f of 0, that makes a0 equal to 1. For condition 2, p prime of x is equal to 2a2x plus a1, and f prime of x is still equal to e to the x. So p prime of 0 has to equal f prime of 0, and that means a1 is equal to 1. The third condition, p double prime of x, is equal to 2a2. F double prime of x is equal to e to the x. You can see why I've used this function, as the derivative will always be e to the x. So p double prime of 0 is equal to f double prime of 0, meaning that 2a2 is equal to 1 and a2 is equal to 1/2. So our polynomial is equal to 1/2 x squared plus x plus 1. We now include our p2 of x in blue. It is still a good approximation around x is equal to 0, but now it is a good approximation further out from 0. Notice as we go out to x is equal to 1 and x is equal to -1, the blue curve and the black curve are still relatively close to each other. So the quadratic is a better approximation than the line. The next step, you guessed it, We are now going to create a cubic that will be an approximation for our function. We will call this cubic P3 of x equal to A3x cubed plus A2x squared plus A1x plus A0. Perhaps now you can see why we've used the coefficients A0, A1, A2, and A3. We still are working with f of x equals e to the x centered at 0. Now there are 4 conditions. P of 0 has to equal f of 0. P prime of 0 has to equal f prime of 0. P double prime of 0 has to equal f double prime of 0. And P triple prime of 0 has to equal f triple prime of 0. Our first condition is that P of 0 equals f of 0, and that means A0 is 1. On the second condition, P prime of x equals 3A3x squared plus 2A2x plus A1. F prime of x is still equal e to the x, and therefore P prime of 0 equals f prime of 0, and A1 is equal to 1. For the third condition, P double prime of x equals 6A3x plus 2A2. F double prime of x is equal to e to the x, and therefore P double prime of 0 equals f double prime of 0 means that 2A2 is equal to 1 and A2 is equal to 1/2. Notice that these coefficients have not changed from problem to problem. But now the third derivative is for P 6A3 and f triple prime of x equals e to the x. So P triple prime of 0 equals f triple prime of 0. 6A3 is equal to 1, and A3 is equal to 1/6. So our polynomial, third degree, is equal to 1/6 x cubed plus 1/2 x squared plus x plus 1. We now graph this in green, and notice that the cubic now is even better at approximating the black f curve. Now it seems that we can go out past 1 and -1 and have a very, very good approximation. You may have seen a pattern in the first, second, and third degree polynomial for an approximation to e to the x. There is one. The nth degree polynomial can be written as 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the fourth plus ... plus 1 over n factorial x to the n. And that approximates e to the x. The more terms we use, the better the approximation is. We will learn this formula and be responsible for it a little bit later in the course. The table shows the accuracy for the first, second, and third degree polynomial for e to the x at values close to 0. At 0, the first degree, second degree, and third degree are all equal to 1, which is e to the 0. However, as we get further away from 1, notice that the third degree polynomial does the best job of approximating the true value of e to the x, shown on the bottom row. So the more terms we have, the better the polynomial does in approximating the true value. So if we wanted to calculate the square root of e, which is e to the 0.5, the calculator does not raise e to the 0.5 power. It takes 1 plus 0.5 plus 0.5 squared over 2 factorial plus 0.5 cubed over 3 factorial plus 0.5 to the fourth over 4 factorial plus 0.5 to the fifth over 5 factorial. It can stop at any point. Stopping at 5 factorial will get the answer accurate to 4 decimal places. So that is how calculators calculate these types of expressions. just by a series of additions and multiplications. In this example, we centered our polynomial at x is equal to 0, but we can also center it at some other number c. These polynomials are called Taylor polynomials, named after the English mathematician Brooke Taylor, and McLaurin polynomials, named after the Scottish mathematician Colin McLaurin. Here is the formal definition of Taylor and McLaurin polynomials. If f of x has n derivatives at x is equal to c, where we say centered at c, then the nth Taylor polynomial for f at x is equal to c is given by the nth polynomial of x is equal to f of c plus f prime of c times the quantity x minus c plus f double prime of c over 2 factorial times x minus c quantity squared plus f triple prime of c over 3 factorial times the quantity x minus c quantity cubed plus plus the nth derivative at c over n factorial times x minus c to the nth power. If c is equal to 0, centered at 0, that means that the nth Maclaurin polynomial for f is given by the nth polynomial of x is equal to f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed plus plus the nth derivative of f at 0 x to the n over n factorial. So the Maclaurin polynomial centers at c equals 0, and the Taylor polynomial will center it at some other value other than 0. But the formulas are the same. In number 2, we're given that f of x equals the natural log of x minus 1, and we're asked to find the first, second, third, and fourth degree Taylor polynomials centered at c is equal to 2. The best way of doing this is creating a table. We start with f of x equals the natural log of x minus 1 and calculate f of 2, which is the natural log of 1, which is 0. So our 0 degree Taylor polynomial is simply 0. It's not something we find very often, but we do it to establish the pattern. We next take a look at f prime of x, which is 1 over x minus 1. F prime of 2 is 1. So therefore our first degree Taylor polynomial would be 0 plus 1 times quantity x minus 2. Our second derivative will be negative 1 over x minus 1 squared. At 2, the value of the second derivative is negative 1. So the second degree Taylor polynomial will be what we had before plus the new term, which will be negative 1 over 2 factorial times x minus 2 squared. We continue. The third derivative is 2 over x minus 1 cubed, and the third derivative at 2 is 2. So now our third degree Taylor polynomial is our term that we had before plus the new term, which is 2 over 3 factorial times x minus 2 quantity to the third. And finally, our fourth derivative is negative 6 over x minus 1 to the fourth. Our fourth derivative at 2 is equal to negative 6. So our fourth degree Taylor polynomial is our terms from the third degree Taylor polynomial plus the new term, which is negative 6 over 4 factorial times the quantity x minus 2 to the fourth. We should simplify these Taylor polynomials. And in doing so, sometimes we can see a pattern. So the first degree Taylor polynomial is simply x minus 2. The second degree is x minus 2 minus quantity x minus 2 quantity squared over 2. The third degree will be x minus 2 minus x minus 2 quantity squared over 2 plus x minus 2 quantity cubed over 3. And finally, the fourth degree Taylor polynomial will be x minus 2 minus x minus 2 quantity squared over 2 plus x minus 2 quantity cubed over 3 minus quantity x minus 2 quantity to the fourth over 4. If you look at these, you are sure to see a pattern that establishes a relationship between the degree of the Taylor polynomial and the actual terms. So without taking derivatives, could you determine what the fifth degree Taylor polynomial and the sixth degree Taylor polynomial for this expression would be? So the fifth degree Taylor polynomial will add on the term x minus 2 raised to the fifth over 5. The sixth degree Taylor polynomial will subtract the next term, which will be x minus 2 raised to the sixth over 6. So it seems that the terms will alternate in signs, with the odd degree Taylor polynomials adding on a positive and the evens adding on negatives. And each term is simply x minus 2 raised to the degree over that degree. We sketch all our Taylor polynomials on the same graph, along with our function f of x equals natural log of x minus 1 in a black dotted curve. As expected, P4 is the closest to f of x at x is equal to 3. But beyond that, none of the curves approximates f of x very well. Later in the course, we will find that no matter how high the degree of the Taylor polynomial, these curves will always diverge beyond x is equal to 3. The same occurs on the other side, as natural log of x minus 1 has a vertical asymptote at x is equal to 1, while the others are continuous polynomials. The value of x, where the Taylor polynomial does a good job of approximating the function, is important, as we see in this last problem. Suppose we wanted to use P4 to approximate the natural log of 3. We know that P4 will approximate the natural log of x minus 1 with x minus 2 minus x minus 2 quantity squared over 2 plus x minus 2 quantity cubed over 3 minus x minus 2 quantity to the fourth over 4. We want our x minus 1 to take on the value of 3, and therefore x is equal to 4. Therefore, the natural log of 3 is approximately equal to 2 minus 2 squared over 2 plus 2 cubed over 3 minus 2 to the fourth over 4. And that will be equal to 2 minus 2 plus 8 thirds minus 16 over 4, which is negative 4 thirds. But we know that this is impossible because the natural log of 3 is a positive number. So what's going on here? The answer is, if you look at the graph, that when x is 4, P4 is no longer doing a good job of approximation of the natural log of x minus 1. It only did a good job up to 3, and after that the curves diverged. So it's important to know the values of x where it is okay to use the Taylor polynomial approximation. We will learn how to do this in a later video. In problem 3, you are given f of x equals sine of x and are asked to find the McLaurin polynomials P1, P3, P5, and P7. To start, we create a table, and we look at the functions f of x, f prime of x, f double prime of x, all the way up to the 7th derivative. The function is f of x, so its derivative is cosine x, its second derivative is negative sine x, its third derivative is negative cosine x, and the pattern repeats itself. Since these are McLaurin polynomials, we are doing this at x is equal to 0. So we look at f of 0, f prime of 0, f double prime of 0, etc. And we see that we also get a pattern, 0, 1, 0, negative 1, and then it repeats itself, 0, 1, 0, negative 1. We are now ready to write our McLaurin polynomials. P1 is simply 0 plus 1x. P2 will have its second degree term with a coefficient of 0, which means we do not need it. So there is no P2. We switched immediately to P3, and now we get x minus the coefficient, which will be negative 1 over 3 factorial x to the third. There is no P4 term, and therefore P5 will be x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. There is no 6th degree Taylor polynomial, so we now move to the 7th and we get x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the 7th over 7 factorial. Hopefully you can begin to see the pattern. We now show the graph of our sine function in a dotted black curve, and P1 in red, P3 in blue, P5 in green, and P7 in purple. Notice that the greater the degree, the better the approximation. And the approximation will be better further out from 0. This is generally true with the sine curve, and if you ask for a very large McLaurin polynomial, you would get extreme accuracy, no matter what value of x you chose. We now see this with our calculator. If we put in the function y1 equals the 7th McLaurin polynomial, x minus x cubed over 6 plus x to the fifth over 5 factorial minus x to the 7th over 7 factorial. By the way, factorial is located in the math probability menu. You will find that if you took the value of sine of 0.2, where 0.2 was in radians, you would get the value 0.19866933308. And finding y1 of 0.2 would give you exactly the same thing. So starting where we began, to try to take the sine of 37 degrees, we look at P5 of 37 pi over 180, because 37 is in degrees and this function uses radians. And we get an answer. And we look at P5, P7, P9 until we do not see a change in the answer. And notice that when we get to P11 and then to P13, we do not get a change. That means that the answer is accurate to 10 decimal places, and that's what the calculator will display for the sine of 37 degrees. Let's do the same with f of x equals cosine x. We want the McLaurin polynomials P0, P2, P4, and P6. We create our table, starting with f of x, then f prime of x, and f double prime of x, moving up to the 6th derivative. And our function is cosine x. Our first derivative is negative sine x, negative cosine x, sine x, and we repeat. So f of 0 is 1, f prime of 0 is 0, f double prime of 0 is negative 1, f triple prime of 0 is 0, and we repeat the process. So P0 is simply 1. P1 will have for its first degree term a coefficient of 0, so it's not needed. So we move directly to P2 and we get 1 minus x squared over 2 factorial. The third degree term has a coefficient of 0, so the fourth degree term for P4 will tack on a positive x to the fourth over 4 factorial. The fifth degree term will have a coefficient of 0, so the sixth Taylor polynomial at x is equal to 0 will now tack on a negative x to the sixth over 6 factorial. Again, we see the graph of cosine x as a black dotted curve, and we also then see P0, P2, P4, and P6. Notice that as our McLaurin polynomial gets higher in degree, our accuracy gets greater further out from 0. Using the calculator, we enter P6 for y1. Y equals 1 minus x squared over 2 plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. If we calculate cosine of pi over 3, we know that to be 0.5. Using our P6, we get 0.49996. So using the sixth degree, we have accuracy to 4 decimal places. If you want more accuracy, then up it to P8, P10, P12, etc. So let's go back to our introductory problem. Number 5 reads, we have f of x equals 16 square root of x. We would like to approximate f of 0.8. We choose to use P3 to do so. Notice that we did not specify where to center our Taylor polynomial. More about that in a second. No matter where we center it, we still have to take derivatives. So we know that f of x is equal to 16 square root of x. F prime of x is equal to 8 over the square root of x. F double prime of x is equal to negative 4 over x to the 3/2 power. And f triple prime of x is equal to 6 over x to the 5/2 power. Where to center P3? There are two factors here. One, we want to center it close to 0.8. Secondly, we want to center it at a value where it is easy to plug in x in our derivatives. After all, if we use a number like 0.5, we're then having to take the square root of 0.5, and that is the object of the entire lesson. Clearly, the best place to do this is at x is equal to 1. It is close to 0.8, and it is easy to take the square root of x and x to any power over 2. So now we plug 1 in to f and its derivatives. So f of 1 equals 16, f prime of 1 is equal to 8, f double prime of 1 is equal to negative 4, and f triple prime of 1 is equal to 6. So we're now ready for our third degree Taylor polynomial. That is equal to 16 plus 8 quantity x minus 1 minus 4 over 2 factorial x minus 1 quantity squared plus 6 over 3 factorial x minus 1 quantity cubed, giving f of x, which is 16 the square root of x, is approximately equal to 16 plus 8 quantity x minus 1 minus 2 x minus 1 quantity squared plus x minus 1 quantity cubed. Therefore, f of 0.8 is approximately equal to 16 plus 8 times negative 0.2 minus 2 times negative 0.2 squared plus negative 0.2 cubed. and that gives 14.312. If we actually take f of 0.8, we get 16 times the square root of 0.8, which is 14.311. So we are accurate to 0.001. The graph of f of x equals 16 square root of x is shown in blue, and the third degree Taylor polynomial centered at x is equal to 1 is shown in red. Notice that the red Taylor polynomial curve is fairly accurate within approximately 0.5 on either side of x is equal to 1. If you want more accuracy, then go up to P4 or P5 because it's really not that much work. Once you understand the structure of Taylor polynomials, there are a number of ways that testers can determine whether you truly understand it. Number 6 states, let f of t be a function that has derivatives of all orders for all real numbers. If f of 0 equals 5, f prime of 0 equals -3, f double prime of 0 equals 1, and f triple prime of 0 equals 4, we want to write the third degree McLaurin polynomial for f, and then approximate the integral from -1 to x of f of t dt. Since we know the value of the function at 0 and its derivatives at 0, writing the third degree McLaurin polynomial is easy. F of t will approximately equal to 5 minus 3t plus 1t squared over 2 factorial plus 4t cubed over 3 factorial. And this gives 5 minus 3t plus t squared over 2 plus 2t cubed over 3. We can now integrate that expression from -1 to x. And we get the integral from -1 to x of f of t is approximately equal to the integral from -1 to x of 5 minus 3t plus t squared over 2 plus 2t cubed over 3 dt. Integrating, we get 5t minus 3t squared over 2 plus t cubed over 6 plus t to the fourth over 6 evaluated between -1 and x. And plugging in x and -1, our final answer is 5x minus 3x squared over 2 plus x cubed over 6 plus x to the fourth over 6 plus 13 halves. Number 7 reads, let f be a function having derivatives of all orders for all real numbers. The fifth degree McLaurin polynomial for f is given by P5 of x is equal to 1/2 x to the fifth minus 2x to the fourth minus 4x to the third minus 8x squared plus 10x minus 2. We'd like to find f prime of 0, f triple prime of 0, and the fifth derivative at 0. In number 6, you were given values of derivatives at 0 and asked to write a third degree McLaurin polynomial. 7 is the reverse. You are given the fifth degree McLaurin polynomial and asked to find the values of derivatives at 0. So, f prime of 0 must be 10 because that is the coefficient of the x term. F triple prime of 0 over 3 factorial must be the coefficient of the x cubed term, which is -4, making f triple prime of 0 equal to -24. And f fifth derivative at 0 over 5 factorial has to equal the coefficient of the x to the fifth term. And therefore, the fifth derivative at 0 is equal to 5 factorial over 2, or 60. In number 8, you are asked, what is the coefficient for x cubed in the Taylor polynomial for f of x equals x natural log of x plus 1 about x equals 0? Two things here. First, When you're asked about the Taylor polynomial about x is equal to 0, you're really being asked about the McLaurin polynomial, just another way of saying it. Second, you're not asked to generate the Taylor polynomial. You're just asked for the coefficient of x cubed. So we take our derivatives. F prime of x by the product rule is x over x plus 1 plus the natural log of x plus 1. The second derivative is 1 over x plus 1 quantity squared plus 1 over x plus 1. And the third derivative is negative 2 over x plus 1 quantity cubed minus 1 over x plus 1 quantity squared. So the third derivative at 0 is equal to negative 2 minus 1, which is negative 3. So the coefficient for x cubed is negative 3 over 3 factorial, or negative 1/2. In number 9, you are told that a function has derivatives of all orders at x is equal to 0. Let Pn of x represent the nth degree Taylor polynomial about x is equal to 0. It is known that f of 0 is equal to 8, and P1 of 3 is equal to 5, and P2 of 3 is equal to negative 11, and you're asked to find f double prime of 0. Let us start by finding P1 of x, which is equal to f of 0 plus f prime of 0 times x. So P1 of 3 is equal to 8 plus 3 f prime of 0, and we know that that is equal to 5. That means 3 f prime of 0 equals negative 3, and f prime of 0 equals negative 1, and that allows us to write P1 of x to be 8 minus x. P2 of x is equal to f of 0 plus f prime of 0 x plus f double prime of 0 x squared over 2. So P2 of 3 equals 8 minus 3 plus f double prime of 0 times 3 squared over 2, and that has to equal negative 11. So 5 plus 9 f double prime of 0 over 2 equals negative 11, meaning that 9 f double prime of 0 equals negative 32, and f double prime of 0 is equal to negative 32/9. Problems like 8 and 9 show up on the AP exam quite a bit in the multiple choice section. Number 10 reads, let y equal f of x be the particular solution to the differential equation dy dx equals natural log of y plus 4 inverse tangent of y with f of 0 equals 1. We want to find the second degree McLaurin polynomial for f about x is equal to 0. We have a formula for dy dx, so dy dx at the point 0, 1 is the natural log of 1 plus 4 inverse tangent of 1, which is 0 plus 4 times pi over 4, which is equal to pi. So the second derivative is 1 over y plus 4 over 1 plus y squared times dy dx. So the second derivative at the point 0, 1 is 1 plus 4 over 2, which is 2, times pi, or 3 pi. So P2 of x is 1 plus pi x plus 3 pi x squared over 2. Again, this is the type of problem that shows up on the AP exam because it really tests your knowledge of how Taylor polynomials are constructed. Understand the cartoon now?